All right, let's get going. So you did the homework for this week, and it's going to be so this week is going to be a little bit different. You are each going to get an email this week. Each of you is going to get an email in about 1 hour from now. It's an automated email from the Canvas system, and it's going to ask you to review the assignments of two of your classmates. Okay, two of your classmates. So what I want is before next week, um, please do the peer review. Okay, do that peer review. You have to go in, take a look at the assignment, and give them a grade. Please note, you get 1 point for doing each of those peer reviews. So if you do both the peer reviews, you get 2 points. Your homework assignment is only out of 4 points. So the peer review is actually half the weight of your homework assignments. That's pretty crazy. That means there's a lot of students every semester who are like, they do the homeworks kind of, at the last moment, but they don't do the peer reviews. And they're missing about a third of their assignment grade. So an easy way to get a fairly good, like a third of your grade this semester for almost free is do those peer reviews. All right. You will get points for it and you'll get a good grade. If you don't do them, you don't get points for it and you suffer for no reason. The peer review takes, honestly, people tell me it takes like within 10 to 20 minutes, easy. Because you just look at somebody else's assignment, you just did the assignment, you look at it and you go, yeah, that looks right. or nope, you forgot to do half of it. Like, it's pretty easy to do. All right. And what I ask is, you'll be asked to leave a comment on each assignment. In the comment, write the grade, like 1, 2, 3, 4, 5, like write the number, and then give a small reason for the grade. Okay. So the grades I'm asking you to give are from like 0 to 5, or really like 1 through 5. If somebody didn't submit anything, it's a 0. I want to be clear about something because I'm getting this question a lot already. 4 is 100%. 4 means everything is correct. Everything, they tried to do everything. Everything is correct. It looks okay. All right, that's 4. If you get a 4 on all your assignments, you're going to get you're going to get like an A score easily this semester, if not an A plus, okay? Assuming you did participation and peer reviewing and everything. You're golden if you get 4s, no problem. So don't complain to me that I only got a 4. That's 100%. All right? Now, if you feel completely blown away by what you see, like if you see somebody's report and you go, "Whoa, that looks amazing." Like the formatting is, I don't mean like it's like super colorful necessarily. I just mean that it was extremely pleasing to look at. You could find everything very easily. You almost feel like you could learn a little bit about how to do formatting well by looking at it. If you feel that way, go ahead and give them a 5. Okay, so 5 means, wow, excellent presentation. 5 can also mean that they did the solution in a very clever, interesting, and understandable way. Like you see their solution and you went, whoa, that's not the way the professor showed it, or that's not the way I would have thought to do it. That's really, really smart. Like, I wish other people could see this. Then you give them a 5. When you give them a 5, it gets our attention. We go and go, what the hell's going on? Why did this person get a 5? So don't start handing out 5 to all your classmates, okay? Because then we have to like kill this bonus point if everyone's abusing it. But give it sparingly. Give it when you're really, really, really impressed, okay? Otherwise, give a 4. That's 100%. That's like the highest grade in the class typically, okay? So 4 and 5. Any questions between 4 and 5? You give a 4 if everything is great. You give a 5 if you're blown away and you want to signal to us, please come and take a look at this. I think this is worth for the professor or TAs to take a second look at this because it's so good, all right? That's a 5. What's a 3? A 3 is, look, they tried everything, but they made some mistakes, okay? They made some mistakes, but they tried everything. It's a 3. You could also give them a 3 if the formatting was absolute rubbish. Like they just, gave you a long R script and you couldn't read anything. Like if it was completely like effortless, you can give them a 3. Like if you had to put effort into understanding what you're looking at, you can give a 3. Okay? Or if, and I said, but otherwise, if they make minor mistakes, that's another reason to give a 3. All right? You can give a 1 or a 2 typically try not to give ones unless you feel completely insulted by what you're seeing. But two means they actually didn't do the whole assignments. Like they maybe got halfway through and then I don't know, ran out of time or something. They didn't do it. Or if it's a late assignment, I think Canvas will tell you this is a late submission. If it's a late submission, go ahead and give it a 2 right away. You don't have to think about that. Even if everything's great, give it a 2. All right. So that's the way we're going to work. 2 is for late or missing parts. 3 is for minor mistakes, but they tried everything. 4 is it was perfect. Everything was it looked good and everything was correct. 5 means, hey, everyone, you should take a look at this. It gets our attention. We'll come take a look. Okay. And remember, give a score in the text box you're given. Give a score and then give us a brief reason why. If you're just giving scores, then we figure you're just like randomly picking numbers. Okay. Give us a brief reason why. If you found a mistake, tell us what you think the mistake is. On the other hand, on the other side, once you get your peer reviews, you are welcome to challenge them respectfully. Be respectful to each other. All right. Say, whenever you grade an assignment, give a compliment and say what you liked about it, and then if there's something they could do better. When you receive it and you feel like they made a mistake or it's unfair, write respectfully that you disagree and you think you should have gotten a different grade. Okay. And I believe the other part, I believe the reviewers are allowed to kind of go back and forth. But if there isn't much of a back and forth, then the TAs and I will decide how to settle it ourselves. Okay, so you're allowed to have a rebuttal question.
Can we rate 4.5 or 3.5?
No, just give a 4 or a 5. Okay. Uh, no, that's a good question. That's actually a really good question because we're talking about scales in this class, right? No, this is a uh, pure integer scale here. So yeah, just give a 3, 4, or a 5 for the most parts. All right. Yes, question.
So the grading is anonymous, like I can know who
Ah,
is
yes. The grading is anonymous. You will not know who reviewed you, which is also why I asked you not to write your name on the report, so that it's also double blind kind of. Now I notice many of you have your ID in your Canvas username. If you want to be anonymous, remove that ID from your Canvas username because otherwise anybody can just search and see who that person is. So my suggestion is if your Canvas username has your student ID in it, remove it. Just leave it your name. Okay? Yeah, but it should be blind both ways. Okay? And anyway, we will, at the end of the day, the TAs and I will see if there was a dispute or a rebuttal and we will settle it ourselves. All right? Okay. Question. No, it should not. Oh, it's because it's me or the TAs. That's why. Yes, yes. But from now on, you should not get a comment. You should not see a name in the peer review. Okay. You might see my name. Okay. By the way, TAs. That reminds me. If we're leaving a comment, I've set it up to be anonymous. So maybe you want to write TA colon, and so people know it's a TA, not some random person talking to you. Okay. All right. Cool. Any questions about this? This is in your handouts. Yes. Question.
if there are some guy have some minor mistakes, but at the same time he gives some number solution. Should I give him 1 point or 3 points?
Wow. Yeah, good question. I don't know. Surprise me. Do what you feel is right. Leave your justification. Okay. Remember, they always have a chance to dispute it and get points back. So don't feel like they're going to lose points forever because of you. And don't forget, oh, by the way, I said two, you will grade 2 people. That means 2 people will grade you as well. So if there's no dispute, we will take the average of those 2 scores. Someone says 5, someone says 3, you get a 4. Okay. All right. But if there is a big discrepancy, I do warn you. If we notice a big discrepancy, like somebody like if you notice that an assignment is if somebody noticed an assignment is late and gave it a 2, or the assignment is incomplete and gave it a 2, and the other person gave it a 5, I've got some bad news for you. We're gonna find out who gave it a 5, and we're going to or a 4, and we're going to you may not get your points for that peer review because clearly you didn't do a peer review, okay? So pay attention and give like the careful thing. There was another question here. Yes. So yeah, if you mention somebody's ID and say they significantly helped me, I mean, they have to write it, not, if you help somebody, they have to write it that this person significantly helped me. Um, we're not going to give you one bonus point for every assignment because then, students are just going to get together and credit each other all day long. All right. So, but if someone does, then at the end of the semester, there's going to be like maybe a 0 1 2 or maybe like 0 1 2 or maybe 3 points altogether for your helpfulness over the whole semester. Okay, but please, we do ask, don't just like give each other's names and both try to get credit, because you're just kind of inflating the score, and it just hurts everyone to do that. Okay, so okay, let's give it a shot. Ask questions as we move along every week. If you don't like something, let me know. When I first started this, it was quite a bit different. The first semester I tried this, people hated it. But every year, people liked it more and more. And I'll I'm being totally honest here. In the last few years where I tried this, people told me this was one of the favorite parts of the whole class for them, because they said looking at other people's assignments, they learned so much more about how they could have done it, or how well they did it. But so it really helped people. So okay, moving on. Oh, if you are not receiving notifications from Canvas about people discussing stuff on Canvas, please change your notification settings. Canvas has notification settings, like you basically go to your avatar picture here, okay? And you choose notifications, all right? And then pick the things you want to be notified about and change its notification setting to notify immediately. In particular, make sure that these three things you're notified immediately. Announcements, which means I'm not going to email you all when I have a big announcement to make. I'm going to do it on Canvas. So if you don't check Canvas, you're not going to get the announcement. That could be a big problem. So set the notification that announcements, you get notified immediately. Course content, this is when I add stuff, your homework assignments and stuff, when I upload them, which will be tonight or tomorrow morning, you ask to be notified immediately. Discussion posts, when people are discussing, I think it really helps to be notified immediately, because there might be something that you ask and somebody else has clarified, and it'll tell you right away, hey, somebody replied. Okay, so change your settings to be notified immediately on Canvas. I talked to my TAs, and for whatever reason, they all have different settings. So don't assume you're getting notified of anything. Okay, please go change these settings. All right. Just a quick show of hands. How many of you are getting notified every time somebody comments, like right away you get an email? Oh, almost nobody. So please do go change those settings. All right. um, you never know when somebody's going to solve your problem. I'm sure you'd like to know when it's solved, right? All right. Okay, cool. Moving on, moving on, moving on. So let's just talk a little bit about statistics and the stuff that makes statistics statistics, because otherwise we're just doing math. Um, little quiz time for a real life quiz. Okay, get ready. On your handout, there's a little link here. Click the link. Okay, do what you want. I'm gonna go find that link here. Okay, I provided you a link. It's a little simulation. It's a really fun little simulation that's online. All right, pretend not pretend. I'm telling you, this is a population distribution. This black distribution up here is a distribution of some variable in the population, meaning it's the data you wish you could have. Like, let's say it's the height of everyone in Taiwan, every single person in Taiwan. Of course, you can never have that data, because if you were to go door to door, before you finish surveying all of Taiwan, somebody will die, somebody will be born. You will never have like everyone's data, obviously, right? In a few limited situations, you might, but by and large, you never have everyone's data. Um, and I want to make a point about this. I often have people who are really into big data, and they're like, no, I got all the data. Like, I got all the customer data, all of it. And I'm like, yeah, but what about the customers who haven't come yet? Like tomorrow's customers, you don't have them. Like when you're describing a population of interest, is usually much more than the data that you have. So even if you're doing analytics on some company's sales, you're typically trying to extrapolate to sales that you haven't seen yet, like tomorrow's sales as well, right? So, but imagine you had all the data and it looked like that. It was a beautiful, normal distribution. And imagine you took a small sample of five elements from the population. Okay, where would the mean be? By the way, the mean of this data is this little pink line here. Okay, if I took a sample of five elements, where would the mean be? Let's try it. Click. 1, 2, 3, 4, 5. Bang. This is the mean of that sample of five. You notice it's not exactly the mean of the population. Let's try another five. Okay, let's try another five. You get the picture, right? You can keep sampling again and again, and each sample will get a different mean. Meaning, imagine for a moment that there were many different researchers, and each researcher was sampling independently of the other researchers. Each one of them would get a different sample, each one of them would get a different mean, right? On average, where should the mean of all these means be? All these sampling means. What should be the grand mean of all these sampling means? Take a guess. What's that? Yes? I heard something. Do you understand what I'm asking? Just take a guess. The population mean? That's a good guess, right? I hope that's true. Otherwise, what the hell are we doing here? Let's speed it up. I'm going to take five samples at a time with every click without the animation this time. You will just see their mean appearing quickly. Five more samples, so five more means. Five more samples, five more means. Five more samples, five more means. Each of these blue things is one of the means that somebody computed, right? You see that the means of these different researchers is beginning to take its own distribution. The statistic, the mean, seems to have its own distribution. If I take a lot of samples and the mean of each of those samples, what will the distribution of the means look like? Take a guess. If the parent is a normal distribution, what do you think this distribution of means is going to look like? Say it louder. Normal? Who said it? Let's try it. I'm going to take 10,000 different samples, not a sample of 10,000. I'm going to take 10,000 samples of five. All right. And I'm going to show you all their means. Boom. It's beginning to look really normal, right? Beautiful. So when I have a normal distribution in the parent population, which we discussed a moment ago that we sometimes have, but we don't have, I don't think we have it that often, okay? But if we have a normal distribution, then the mean of the samples, if you were to take thousands of samples, like there was 1,000 researchers each doing their own sample, on average, their means would be the population mean, and their means that they're collecting, some would get a weird mean out here or here, but most would get a mean around here. The sampling means would also follow a normal distribution. How awesome. Okay, now let's try this to see if you're paying attention. I'm going to create a funky looking distribution here. All right. Asymmetric. And let's try this exercise again. If I was to take one sample of five, the mean is there. Another sample of five, the mean is there. Okay. Now, if I took five more samples of five, the means are like this. All right, question. On average, if I was to take thousands and thousands of samples of five, on average, where would their means be? The mean of the means. Right under, who said that? Raise your hand. Right. The it would you would hope it would be the population mean, right? Second question, you know it's coming. What's the distribution of the sampling means going to look like? Think about it for a second. Okay, second over. What's the distribution of the sampling means going to be? How many of you say it'll still be a normal distribution? How many of you say it'll be a distribution that's similar to the population distribution? A few hands. Let's try it again. How many of you think it'll be a normal distribution? How many of you think it'll be a distribution similar to the population distribution? Okay, cool. Only one way to find out. Flip the textbook page. Okay, let's keep doing this, and I'm going to do 10,000. I'm going to take 10,000 samples now. Boom. 10,000 more, 10,000 more, 10,000 more, 100,000. Kind of crazy. The mean does not follow the distribution of the original distribution you had. Huh. Maybe because this is still kind of bell-shaped. Okay, fine. Let's choose a completely like, I don't know, something like this. I don't even know what the hell that is, okay? Let's do it 10,000 at a time. Boom. Uniform distribution. Oh, uniform distribution, more or less. 10,000 at a time. Boom. Weird jaggy distribution. Wow. The sampling mean follows a normal distribution. And this is why we like normal distributions, actually. It's not because data is ever normal. Data is hardly ever normal. I don't think you're going to get too many actual data sets from me this semester which are normally distributed. Not because I'm trying to be a jerk, it's because I can't find many. All right? So why are we so obsessed with the normal distribution? It's not because data is normally distributed, it's because the statistic called the mean is normally distributed. When you collect data, you're getting one mean. But if 1,000 people were to collect data from the same population, the mean of all these researchers would be normally distributed. That's what we love about the normal distribution. Okay, it's the statistic of called the sampling mean, which is normally distributed. Are we good with this? Fantastic. Do you notice something else? That when I make a very wide distribution, this is a very wide distribution, but the mean, the sampling means have a much narrower distribution. The sampling means don't have a wide distribution, they have a narrow distribution, which is great. Even though my data can be very wide, the means on average are not as wide. They're much narrower, right? That's fantastic. So as you know from your previous stats classes, the sampling means across all samples will have a normal distribution. What is going to be the standard deviation of the sampling means? Not the standard deviation of the data. All right, let's say 1,000 researchers have collected this data and they've got 1,000 means. So now forget the data. I'm only interested in the means. That's the new data, is the means. What's the standard? The mean of the means we said is going to be probably the population mean. And it is. That's why stats works. Okay. What about the standard deviation of those 1,000 means that 1,000 researchers got? What's the standard deviation of that going to be? Is it going to be as big as the parent population standard deviation, bigger or smaller? How many of you say that the standard deviation of the sampling means will be smaller than the parent distribute data's means? Smaller. How many of you say it'll be roughly the same size? How many of you say it'll be bigger? Okay. Either you're not playing with me or you're all correct. It'll be smaller, obviously, because this is a much narrower distribution. So it'll be a smaller standard deviation than the parent data's distribution. So the distribution of the sampling statistic, the mean statistic, is going to be much narrower. And in fact, I'll just jump to the formula that you've all seen. Oh, that's not written correctly. Let's go to the next page. Hope it's written better. Yes. The standard deviation of the sampling means is called the standard error. Okay, so when we say standard error, we're talking about a standard deviation, not of data, but of a statistic, the sampling means. All right, and the standard deviation is simply the standard deviation of the data based on a single sample, not the standard deviation of the actual data. Like if you have a sample of data, your estimate of the parent's standard deviation, the sampling mean, your samples, excuse me, your sample standard deviation divided by the square root of the size of your sample is going to be the standard error. All right. So basically, it means that this implies that if I have just one sample, not 1,000 samples, I can still say some pretty interesting things about the parent population. I can say that I expect roughly that my sample's mean will be the parent population's mean. But what's more important and interesting is I can kind of tell you how wrong I might be because the standard error kind of tells you like that the parent population should be close to my mean, but around so many standard deviations, standard errors of my mean. All right. Okay. So you've seen this all before in a previous class, I'm sure, but let's just play with this again. When I calculate one sample and I get its mean, I can compute something called a confidence interval, right? For example, the 95% confidence interval is the mean of my sample plus or minus 1.96 standard errors, all right? It's telling you, given my sample mean, where could all the other sample means be? Or actually, where could the population mean be? And we expect with what we call 95% confidence that the parent's mean will be within 1.96 standard errors of my sample mean. Okay? Confidence is a terrible word to use because it's actually not that, but we'll come back to that in another class, in another session. Let me try to visualize what this looks like. Before I do, the 99% confidence interval of the population mean is the mean that you estimate from your sample, right? This fellow right here, your sample mean plus or minus about 2.58. Is that right? Yeah, about 2.58 standard errors to the left and right. Okay, so you're saying this is my sample's mean, but I think the population mean is close to it with decreasing probability as I go away from my sample mean, but to the left and right by either 1.96 standard deviations left or right, or with 99% confidence, I could say with 2.58 standard deviations left and right, okay? Let's try to visualize what this looks like. So I'm going to go to some code that I will give you for your homework assignment. We're done with this. Let's go to confidence intervals. All right. For your homework assignment, I'm going to give you two functions to play with. I mean, I'm giving you this code. It's not the best code in the world, but it's mine, so don't say anything bad, okay? It'll hurt my little feelings. All right. So these two functions, once I've loaded them, I can call this function in particular, visualize sample confidence interval, CI. And this is what it's going to do. It's going to take a sample from a population, and based on only that sample, oh, excuse me, let me say this again. It's going to take, in this case, 100 samples from a population. The population size is 10,000, but I'm going to take 100 samples of size 100, and I'm going to visualize the mean and the standard errors of each of those samples. So pretend 1,000 researchers, no, not 1,000, pretend 100 researchers each collected 100 samples from the same population. Let's see their 100 means and let's see the standard errors, the 95% confidence interval and the 99% confidence interval of those 100 researchers. So when I hit enter, it'll show that for me. Okay. I can, if I run this function again, it'll show it for me again, and every time it'll kind of do it slightly differently. Okay. Now, on average, I'm going to show you what I think is, roughly speaking, an average image. The average image should look something like this on average. It'll look a little bit different each time, but on average, this is the picture that kind of emerges. Okay. So you see here straight horizontal lines. Each line has a dark dot somewhere in there, right? The dark dot is that researcher's sample mean, right? So as far as that researcher is concerned, that's their estimate of the population mean, right? So this first researcher up on top, that's represented by this line, their mean was here, and they guess that's their estimate of the population mean. They're wrong, because the population mean is this dark black line running through the middle. The second researcher, their guess of the mean is on the other side. They're also a little bit wrong. The third is here, the fourth is here, the fifth is here. As you can see, these black dots are kind of distributed around the population mean, right? What else can we see? Each line, like this blue line, has a dark component and a light component, okay? The dark part of the bar is the 95% confidence interval. Meaning, if that researcher took their sample mean, then took the standard deviation of their sample, and they used it to compute the standard error, then plus or minus 1.96 standard errors to either side of the mean, this researcher with quote unquote 95% confidence is sure that the population mean is somewhere within this interval, within this dark band. They could be wrong, but they're 95% sure it's there. With 99% confidence, it's the light band from here to here. Okay. Is that person correct? Yes, this person is actually correct. The mean is not their sample mean, but it is within the 95% confidence interval. All right. Now, some researchers, like this poor soul over here who is in red, they're going to be mistaken. Their sample mean is out here. Their 95% confidence interval falls a little bit short of where the population mean actually is. And yet, with 95% confidence, they will say that the population mean must be somewhere from here all the way to somewhere here. Okay? They're wrong, but that's what they would say. They would still be right about their 99% confidence interval. With 99% confidence, yes, it is from here to here. Okay? So on and so forth. So you see in red, I've shown the people who are wrong about either their 95% or their 99%. So on average, out of 100 people, how many people will be wrong about their 95% confidence interval? How many people will be wrong out of 100? 5. That's why it's called the 95% confidence interval. It's not because they're right. It's because if there was 100 researchers, then 95 of them would be right on their computations and 5 would be wrong. Which one are you? You have no idea. If you've collected one sample, you have no idea. Which is why many people don't like the term 95% confidence, because you can be 95% confident and totally wrong. You can be 100% confident and totally wrong. You actually don't know which one of these you are. Okay? But if there was 100 of them, you're praying you're part of the 95 who's correct. Now, I haven't shown it here, but on average, one person should be wrong about the population mean falling even in the 99% confidence interval. On average, right? So, okay. So on average, let me see if I can, oh yeah, here we go. Like this person here, is not only wrong about their 95% confidence interval, they're even totally wrong about their 99% confidence interval. How many people on average will be, actually there's two people in this plot. Oops, that person's also wrong about the 99% confidence. But on average, how many people do we expect out of 100 will be wrong about the 99% confidence interval? One. The other 99 should be right. That's why it's called the 99% confidence interval. Are we okay with this? Little stats review, in case you forgot it. Okay. All right, cool. That's just a refresher of stats. With the remaining time, I've a couple more things to show you. And this is all I want to do. I just wanted to remind you of your elementary stats really quickly, okay? About sampling means, the distribution of sampling means, the grand mean, the standard error, stuff like this. I'll give you a homework assignment on this so that you can, I mean, part of your homework assignment will be asking about this, so just help you refresh what confidence intervals are, okay? And what I'll do is, this is going to be cool, I think, to me, I will let you play with this distribution by changing the parameters, the number of samples, the sample size, the population size. You can even change the underlying population distribution to see how it affects these 100 researchers collecting data. Okay, so you'll get to play around with this and simulate all different types of things, and we'll see what we come up with at next week, what we have realized about sampling and sampling statistics like the mean. Okay. Any questions on this? All right. If not, just take 30 seconds to stretch out and relax. Ah, the easy part of the class is over. The hard part is coming up, okay? All right. Just take a moment to relax. Uh, slowly roll your neck. Slowly. Don't like, professor told me. All right, stretch out a little bit, drink some water. Your stats nightmare is over. Your computation nightmare is about to begin. I've got a few more slides to cover, which will be on something slightly different. All right. Are you relaxed? Are you ready for what's coming? Are you 95% sure you're correct? 5 of you are not ready. All right. Let's look at something totally different. Okay. Enough about sampling means blah, blah, blah. Right. Environments. It's fine. On to the last thing of this class. Okay. I want to go back to something that I hinted at and started with like a couple of classes ago, and I want to go back and see if there's something interesting there. All right. Remember, some time ago, we where are we? No, I should be doing booster basics. Okay, cool. All right. Some time ago, we did this simple exercise where we took a sequence of data, like the numbers, what is this? Like the numbers 1 through 20, the sequence of numbers 1 to 22, okay? And we did this funny thing with it. We sampled from it, right? We took some data and we took a sample of the data. And we took the sample in a very interesting way. We said sample from this data, excuse me, sample from this sequence of data, all right? But with replacement, with replace equals true, which means pick a number, tell me what it is, put the number back in the sequence. Pick again. It could be the same number, it could be a different number, but randomly, with the uniform distribution, like uniform randomly, pick numbers from this sequence, okay? And first of all, if replace was not true, right? What would my resample look like? If I was not doing replacement, what would this resample look like? Anybody? Say that? The same numbers? It would be the same numbers in a different order. And in fact, if I sorted them it would be exactly the same as the sequence, right? So to make it interesting, let's do true. We're going to sample from this sample the same length as this sample, but with replacement. Okay? What does this look like? What we saw last time, and you know what, I'm going to sort it so that you can kind of, because the original data was in sorted form. So let's sort it. What does this data look like? It looks a little bit like my original sample, right? Except some numbers are going to repeat, like 2 repeats 3 times, right? 2, 2, 2. So 2 repeats 3 times. In the original sample, it was only there once. But some numbers, like 4 and 5, have just disappeared. I didn't get them, right? So what I kind of get is an approximation of my original sample, but just a little bit different. Okay. Let's try it with another one. This time, I'm going to use a sample which has, can you see it? It's got kind of a bell-shaped distribution to it. Why? The numbers on the either end occur very infrequently. 1 and 7 occur once, 2 and 6 appear twice, 3 and 5 appear 5 times, and the number in the middle is the most likely to appear. It appears 4 times. If I was to, oops, if I was to plot the density function of this rep sample, it would look like a bell-shaped distribution. It's not a normal distribution, but it would look like a bell-shaped distribution, right? And if I was to if I was to draw the histogram, Sturgis is fine. Oh, this is a little bit funky. R has a little bit of problem here. Is there a shortcut to telling it what function I want? Like Friedman-Diaconis or whatever? Is there a way to do it? Breaks. Hold on, let me take a look. Question mark histogram. Can I make this histogram a little bit better? Can you say that louder? Oh, you're not sure. He's mumbling, he's not sure. Okay. Um, I thought there is a way to do it, like without using my formula for it. Let's search. Um, Histogram R Friedman-Diaconis. All right, number of bins. Oh, I should see it in R. Um, Someone's got to tell me how to do it. There should be a simple way. Anyway, doesn't matter. Let me just jump to R, and let me do it like this. Let's draw the histogram, and I'll say breaks equals 8, 9, 10. Does it make a difference? Okay, you see a little bit of a bell-shaped distribution now, right? Okay, cool. So my point being, I am taking this sample of data with a bell-shaped distribution, and I'm going to resample from it, all right, with replacements. What am I going to get? Oh, and let me sort it, so because the original data is in a sorted form. It's not perfect, but you do notice that the numbers at the edges of the original sample, which were very infrequent, are also infrequent in my sampling of it, in my resampling of it, right? Because they didn't occur very often, so when I resampled at random, they also occurred infrequently. One appears twice, but not more than that. Numbers towards the middle, like 3, 4, 5, they occur more often in my resampling of it, right? And in fact, 4 appears exactly 4 times as it did in the original data. So what's interesting here is that I take some data, which is maybe even a sample, and I resample from it, and it seems to follow a similar distribution. And we can kind of visualize that here. So if this was the original sequence that I was sampling from, if I look at the density plot of the resample, it's got this like, it's got a similar-ish shape. It's a little bit off, but it's similar. It's at least bell-shaped somewhat, okay? So one of the interesting things about resampling with replacements is that if we randomly pick elements from a sample with replacement, our new samples will have a similar distribution to our original sample, okay? How, how is that helpful? What can we do with this? Take a look. Let's take situations like, okay, for example, here, I'm going to take a population of data. I'm going to, let's go to the next file over. All right. Okay, I'm already there. Okay, I'm going to create an artificial population, okay, with like A, B, C, D, some parts to it, and a population, all right, and the mean of the population. And this is my population data, okay? This time I'm drawing the population data in a dashed line because typically you can never see the population data, right? You only have the sample that you got. So, but let's pretend that we secretly kind of knew the population data. It looks like this, all right? Now, and by the way, the mean of the population is 242.5. I am going to take one sample from this population. By the way, what's the size of this population? It's about 200, it's about a million, right? It's about a million. I'm going to take one sample from this population, a very small sample, just 300, okay? And so sample 0 will be, oh, population goes in here. I'll fix them as I go along. Sample 0 is going to be the only sample I'm going to take from this population. It's going to be the only sample I will take from this population. And its sample size will be 300, okay? So now let's visualize the density plot of the sample, and let's draw the population mean and the sample mean on this plot, okay? So it looks something like this, all right? So the population that I typically cannot see is this dashed line. My sample follows a similar distribution, even though it's only 300. The population is 1 million, but I'm capturing many of the important parts of the population, right? However, I am wrong at some points, right? Like you see the probability at this point, the population probability is up here, but my sample probability is a little bit lower. Oops, okay? Or at the peak, the population probability was a lot higher. My sample probability is lower. There's a little bump here that I'm also missing. So I'm kind of approximately getting something that looks like the population. Generally, when I sample data, when I get a sample of data, I don't know what the population distribution looks like. I only know what the sample distribution looks like, right? And as you can see, we know we're going to be missing some things here and there, right? Like our distribution is not going to be the same as the population distribution. And we have our the population mean is a dashed line. My sampling mean is a little bit wrong, okay? Now I know we can use some statistics to kind of do like standard error, this and that. Let's try to do this in a non-statistical way, or I should say a non-parametric way. We're not going to use our classical statistics. We're going to try to figure out what's the standard error, and we're going to try to figure out the sampling means and stuff in a slightly different way, a computational way. Take a look. So what I'm going to do now is let's go to the next slide. All right. I'm going to do something a little weird, really weird. This is the part where you really need to focus, okay? I'm going to take that sample that I had. I'm going to pretend I don't have the population for a moment. I only have that sample 0, okay? I'm going to take that sample and I'm going to resample from that sample. I'm going to sample my sample because I don't have the population. And okay, I'll tell you what I ideally want. Ideally, I would like thousands of other samples from the population. But I don't have that because I'm just one researcher. I just have one sample. But what if I treated my sample like it was a kind of population and I kept sampling from my sample? So here you notice I'm saying, please sample from my sample. I'm specifying the length of the sample, which is the length of the 300 with replacement. And I'm going to do this not once, but I'm going to do this 3,000 times. This replicate function over here, replicate, it's a really handy function. You can give it some code and tell it how many times you want it to run it. So in this case, I'm telling it, please sample from this small sample I have and give me 3,000 more subsamples or resamples. All right. So now instead of one sample, original sample, I'm going to have 3,000 samples. But these 3,000 samples didn't come from my population. They're coming from my original sample. Kind of crazy. Let's see what happens. So we're going to run this. Okay. Resample. Ooh, that was quick. I just got 3,000 samples from my sample. Can I see it a little bit? Resamples? No, it's going to be very hard to show it. But I can say resamples, uh, comma one. Okay. This is the first resample. It's 300. You see 295 is 300 elements that it sampled from my original sample 0. Okay. So that was the first resample. There's a second resample. There's actually 3,000 resamples. All right. All gotten from my original sample. Well, how does that help me? Let's try to visualize the distribution of all these resamples. All right. Now remember again, I really feel like a magician now. I don't even have sleeves. Okay. These resamples have never seen the population. They're all being sampled from my original sample. All right. So what I'm going to do is I'm going to create an empty plot where I'm going to where I'm going to visualize 3,000 distributions. So I'm going to draw 3,000 density plots. All right, 3,000 density plots. It may be a little slow, forgive me. To make my life easy, I'm going to use an apply function. I'm going to write my own function called plot resample. So you give me one of the resamples and I will draw the density plot using lines so I don't delete the old plot. I draw on top of the old plots. And I'm going to return the mean of that subsample. Okay. By the way, the color I'm using, this is called RGB. I'm telling the color in red, green, and blue. So I'm asking it for mostly a green color, no red and blue. And this is called alpha transparency. I'm saying make it very light and make the line kind of transparent because I'm going to draw 3,000 lines. I want to be able to like kind of stack them on top of each other and see where it's thick and where it's thin. Okay. So here's my function to draw a single density plot and return the mean of a single distribution. I'm going to now apply this to 3,000 resamples. Forgive me, this is going to take a little while to run, but let's see what we get. It's running. It's running. It's finished, but it hasn't finished plotting yet. You got to give it a few more seconds here. Whoa. I get this very ghostly image. And actually, I'm seeing 3,000 ghosts, right? Because each of these distributions doesn't exist in nature. The original sample 0 I took exists in nature. The population exists in nature. These are 3,000, if you want, like ghost distributions. They've been resampled from my original sample. And you notice they disagree with each other. So, like, they're not all on top of each other. They're kind of like, there's a haze of them. All right. Let's try to plot what we do know about the world on top of it. Here is the original sample, sample zeros, density plots. It'll take a second to appear. That was the original sample zero, okay? And these 3,000 resamples are pulled from that original sample zero. Let's go back to our population distribution. Wait a second. Yeah, I changed my code last night, and I forgot to change it here. Let's look at the population distribution. It's gonna appear in a moment. Whoa. So take a look at what's happening. We said that our original sample is wrong from the population distribution. It underestimates it or overestimates at certain points, right? But do you notice, if I look at my 3,000 samples, some of them are as tall as the population distribution. Some of them are even taller. The places where I'm wrong, there is quite a bit of variation here, such that the population does fall within my ghost resamples, right? Similarly here, notice my original sample underestimates the probability at this point, but my 3,000 ghost samples, resamples, they say, well, it could be as high as here. There's a few wisps up here. You cannot see on the projector maybe. There's a few lines up here. It could be as low as here, okay? So even though I don't have the population, by and large, my ghost resamplings do cover all the possibilities, including the population. That's interesting. What I've done here is a technique called bootstrapping. How many of you have seen or done a bootstrap before in a previous class? Oh yeah, we got a bootstrap fan. Yeah, we'll have a party after class, okay? With 3,000 of our clones, okay? Um, so this is called bootstrapping. And it's called bootstrapping because it's a, oh God, I hate the word, but it's an old English, American English expression, which means, and the physics doesn't even work correctly on this. It's kind of, the expression means like, if you're down on the ground and like, you're on the ground, you're helpless, don't expect someone to come and pull you up. Grab your shoelaces and pick yourself up. So bootstrap means your shoelaces. All right. So bootstrapping means you don't have more than what you have. Use what you have and pick yourself up. All right. So it's called bootstrapping because we don't have population data usually. All we have is a sample. So what we can use is that sample that we have. All right. Um, you'll see this expression bootstrap or boot up in a lot of places, like to boot a computer means to start the computer from zero, like to start it up by itself is called booting for that reason, all right? Or the expression pick yourself up by the bootstraps, maybe like 100 years ago, that was a popular expression. Not so much today, all right? But in statistics, the word bootstrap continues to be popular, all right? And essentially what we have done is a technique where even though we cannot see the population, and we obviously don't have 1,000 other researchers to give us their data, we can use our data to approximate what the other 3,000, 1,000, 1,000,000, whatever I want, other researchers, what their data would have looked like, could have looked like, all right? And what's really cool about this is I showed you the distribution of the resampled data. What about their means? What's the distribution of their means look like? So I've got 3,000 means now, right? Because when I did this, what's the replicate function? When I did this replicate function, I basically, oh, excuse me, not that one. Not replicate, excuse me. When I did this apply function, I ran this plots resample density function that I wrote, and that function returns the mean of each of those 3,000 subsamples. Let's take a look at the distribution of those 3,000 means. All right. So I'm going to start with the population density distribution and the density curve of my sample zero, the data I actually have. Now I'm going to make another function here, which is going to draw, given a sample, is going to draw a vertical line where the mean should be. Okay. And I'm going to now apply this function to the 3,000 means that I have, the 3,000 the resampled means that I have. This ghostly bar is the three, and I'm using, by the way, a gray color. So 0.7.7 RGB, 0.01 transparency. It's called alpha transparency. So I get like a transparent gray line. So I'm seeing a gray bar, which kind of extends out. I don't know if the projector can show you, about this far to the right and this far to the left. Okay. So I'm seeing a wide gray bar with a very thick gray band in the middle. And I'm going to draw in there the mean of all the means, which should be the same as the mean of my sample zero, actually, because these are all pulled from sample zero. And I'm going to draw the population mean. And what you can see, maybe, is that even though the population mean is not the same as sample zero's mean, which is, the mean of all the 3,000 resamples, the population mean is within the range of sampling means that I got from those 3,000 bootstrapped samples. It's in that range, right? Which means that even if I knew nothing about statistics and I only knew how to do a bootstrap, I could get my sample mean, bootstrap it, wiggle it around, jiggle it around to get these 3,000 resamples, and with quite a strong likelihood, the population mean will be in this range. I've used no statistics. I've used no standard errors or anything like that. All right. And actually, let me do one more thing. Let me just plot the distribution as a curve, as a density plot of the 3,000 means. All right. What you're seeing is when I bootstrap, I get a distribution of means, which is a normal distribution. This is a normal distribution. All right. It's almost as good as if I had 3,000 original samples from the population, which I don't. I've resampled 3,000 times from my own sample, and the 3,000 means form a normal distribution. All right. And this shows you kind of like what happens in nature with sampling. So possibly an alternative way of finding confidence intervals, possibly, is not to use the statistics that you know, standard error, but to do it computationally. I can just get 3,000 more means and look at their distribution, and I know that the population mean must be in here somewhere. All right. So this is a glimpse of what we call bootstrapping, and it will give us in the weeks to come an alternative to using classical statistics, because we can jiggle the data around and it will tell us how certain statistics behave, even if we didn't know the formula for it. All right. And I know you're going to protest and say, but we do have the formula for the mean and its standard deviation, its standard error. What if it was a statistic that we didn't have that knowledge about? This technique could help. All right. I will let you play with bootstrapping as the final part of your homework. So this is a major homework. Please don't start at the last moments. There'll be several moving parts to this homework. All right, so please start it as soon as possible. I'll try to get it up by tonight or tomorrow morning. Get started on it right away. Um, and it's going to take you through a range of things. The homework will cover issues in classical statistics, standard errors and means, all the way to bootstrapping to get similar information. And we'll put it all together and make sense of it when we come back to class next time. Okay? All right. Thank you very much. I'm going to finish about 10 minutes early, which is okay. Nobody is going to complain, I think, right? All right. All right. Thank you so much. See you next time.